Right, hi everyone. So my name is Naomi Rowe-Gurney and I'm a PhD student at the University of Leicester. I'm going to be talking to you today about using the Spitzer infrared spectrometer to look at the ice giants, Uranus and Neptune, and specifically their middle atmospheres. And hopefully by the end of the talk, you'll understand what all of that means. So the general layout of today's talk, with a bit of background on the ice giants and observing their atmospheres in the mid-infrared. And then I'll get into what we found in the stratosphere in the Spitzer data that we found this observation, this observed longitudinal variation. Then we'll look at the models we've been using to determine the cause of the variation. So we'll discuss that. And then I'll summarize with an overview of the future work that I'm doing and also the future of ice giants in general. So I'm going to start at the very beginning because I know we have a wide range of people listening today. So the most frequent question I get asked is what makes an ice giant an ice giant? So an ice giant is smaller than a gas giant, the gas giants being Saturn and Jupiter, but they have a similar base composition. So the hydrogen and helium they have in their atmospheres just like them. But the main difference in an ice giant is this high concentration of ices. And by ices, we don't just mean water ice, it's also the heavier elements, anything heavier or with a higher freezing point than hydrogen and helium. And this picture that I'm showing you now is the best guess of what we think might be inside an ice giant. So the outer layers of the clouds and atmosphere is what we're going to be talking about today, but also deeper as we get into the higher pressures and higher temperatures, things start to get a bit weird and you end up with a supercritical water ocean maybe, and then underneath that it gets even weirder and you end up with something called superionic ice, which is this hot black ice that has actually been recreated in similar temperatures and pressures in the labs on Earth. So we do know this stuff exists. And then below that, we think there's this small rocky core. But as I said, this is just our best guess of what is inside. And we know so little about them. There's even speculation that they should be called rock giants and not ice giants. So who knows? So everything we do know about ice giants is from our ice giants in our solar system, so Uranus and Neptune. They are very similar to each other, obviously, because they're both ice giants. They're similar size, they're made of similar stuff, and we think they come from similar origins. They both have ring and moon systems. They both are blue due to the high concentrations of methane in the atmosphere. But they also have a lot of differences. We think that Neptune is our typical ice giant and Uranus is our unique ice giant. So they have differences in their axial tilts, differences in their internal heats, and differences in the activity in the atmosphere. So Uranus being the weird one, that's the one that we're currently focusing on in our studies. So Uranus is at 19 AU, which means it has an 84-year orbit around the sun. And it has this 98-degree obliquity, or this extreme axial tilt. And this extreme axial tilt is why we have done the investigation that we've done with the Spitzer data, because it's a motivation to do the observations in the equinox. And because of the extreme axial tilt, it means there's only two windows, these equinoxes, in every 84-year period to view both the north and the northern and the southern hemispheres simultaneously. So that's during around the equinox, which the last one was in 2007. So the animation in the top right shows what Uranus looks like over that 84-year period from Earth. And the images on the left show the view from Earth from 1997 through to 2017. And so we see the South Pole rotating out of view and the North Pole rotating into view as we go to 2017. And then in the middle, we have 2007, which is our equinox. And that's what we're interested in because this sideways view where we're looking down upon the equator and the rings that edge on is what makes this investigation worth conducting. And the 2007 Spitzer observations that we're going to be talking about were conducted 10 days after the exact equinox. So just a quick detour to Neptune as well. We don't have the same problem with Neptune because it's our typical ice giant. We can see longitudinal variability all year round, all Neptunian year round. And the Hubble images on the left also show that because we have a difference in atmospheric variability, it appears to be more dynamic than Uranus's atmosphere, although we'll come back to why that's important later. So the ice giants are often viewed in the infrared using ground-based instruments, because ground-based instruments are easier to use and they're able to be made much bigger. And they give us a great spatial resolution because of their size, but because of the absorption of the Earth's atmosphere, especially at mid-infrared wavelengths that you can see in the orange images, we have a poor spectral resolution. So usually we can only do 1 or 2 bands in the mid-infrared especially. And that's why we have to go to space. So we use something called Spitzer. So what is Spitzer? Spitzer is an infrared telescope. It was launched in 2003 and it was decommissioned only this year on January 30th. It was in an Earth trailing orbit and it has a 0.85 meter collecting mirror. And that seems quite small, especially considering how big the ones are on Earth, but it's in space. And so we have this uninterrupted view of the mid-infrared. So why is the mid-infrared useful? Especially for sensing atmospheres of our giant planets. It's useful for sensing the middle atmosphere of the ice giants. And by middle atmosphere, I'm talking about the stratosphere and the upper troposphere. So the red arrow on the right-hand side shows the mid-infrared sensing. So all of the images that I'm showing here are of Uranus at different wavelength bands, but this also applies to Neptune. And so different wavelengths are sensitive to different depths in the atmosphere. And so let's start with the visible and the near infrared in blue and purple. So on the right-hand image, we can see that that senses around the tropopause at around 0.1 to 1 bar. And then if we go to the microwave in green, then we're sensing much deeper in the troposphere down to around 50 bars. But then if we look at the mid-infrared, the thermal infrared, then we can look at higher up in the stratosphere and look at those stratospheric hazes as well as the tropospheric hazes, which is why it's so useful. And when I say troposphere, I mean everything below the tropopause in that diagram. And when I say stratosphere, it's everything above the tropopause. So why is the stratosphere so interesting, especially in the ice giant planets? It's because we have this layer of photochemical hazes, and these hazes come from when methane is elevated into the stratosphere. It's broken down into these complex hydrocarbons by photolysis or photodissociation, and these abundances on the right show we have methane in the stratosphere, as well as these more complex hydrocarbons like acetylene and ethane being the main two, and then also some smaller abundances of methylacetylene and diacetylene. And all of these species have been observed using Spitzer. This is the kind of data that we get from the Spitzer infrared spectrometer. An example of Uranus on the left and Neptune on the right. We can see the main features of methane and also some complex hydrocarbons in the features. And the overall shape of the spectrum is governed by hydrogen and helium and the temperature underneath that. And comparing the two, there's a general trend that's the same and similar features, but Uranus temperatures are lower, which is what we would expect. So the data comes from the mid-infrared spectrometer, the infrared spectrometer, the IRS, which is mid-infrared. And we actually have multiple epochs of data for both planets. You can see in the table. And they're all disk averaged though. So that means we have 0 spatial resolution from Spitzer IRS. And so 1 exposure means we only have 1 spectrum. And that's why the equinox is so important for Uranus, because we're looking at how the planet changes as it rotates. So the only way we can do that is over time. And we have multiple longitudes for each epoch. And the previous data that I showed before was a global average with all of the longitudes averaged together. So this investigation is about splitting apart those longitudes to investigate the changes between them. So the 2007 data here is our important data, the one that we're focusing on, because it's the highest quality of data for Uranus, and also it was used in an investigation by Orton et al. In 2014, which gave us some priors to use, which I'll talk about later. So the infrared spectrometer has 4 separate modules with different wavelengths and spectral resolutions from 5 to 37 microns, so firmly in that mid-infrared band. And the modules are fixed, so it takes time to slew the entire spacecraft from module to module. And actually this helps us because instead of having just 4 longitudes, which are shown in the colors in the right-hand diagram, we have 16 individual pointings because of the 4 separate modules as well that take time. So between L1 and L4, in the blue and the purple, you've seen over an entire rotation of the planet. So do we see any differences between these longitudes? And the answer is yes, we definitely do. We see a consistent variation clearly in all modules. And the right plots show the difference in radiance for the entire range of both the high and the low resolution. And we can see a consistent pattern that the L3 in green is dimmer and the L4 in purple is brighter in most bands. So looking at the main hydrocarbon bands in the low resolution, we can see the same pattern here clearly, that L3 and L4 are almost opposite in the hemispheres. So one of them is around the 130 degrees and the other one is around 280 degrees. We can see something is happening between the dimmer L3 and the brighter L4. So to look closer, we've decided to take the bands in the high and the low resolution and found the variation for each species. So the top plot shows the bands that we've decided to use, and the bottom plot shows the contribution of each wavelength to different pressures or altitudes in the atmosphere. So again, I've marked on the tropopause there, so everything above it is the stratosphere and everything below it is the troposphere. So if we take an example species, let's take methane. Methane contributes to the stratosphere at around 10 to the minus 4 bar. And CH3D, which is monodeuteurated methane, and the hydrogen-helium continuum, they both are contributing to the troposphere. So if we look at the variation of these specific species, we can see that the methane, as the black points, are varying by up to 15%. And the tropospheric species, CH3D and the continuum, have a negligible variation. So we can see a stratospheric variation, but not a tropospheric variation. And we see the same pattern in other stratospheric hydrocarbons. So these are the others, so ethane, acetylene, methylacetylene and diacetylene. And we can see that they have up to a 10% variation. And we also see the same variation in the hydrogen quadrupole, which is present in the upper troposphere. And we can also see that it's consistent after that one full planetary rotation that we were talking about. So we know we have this stratospheric variation, but what could be causing it? So to start trying to detangle what's happening, we're using something called NEMESIS. NEMESIS is an optimal estimation retrieval algorithm developed at the University of Oxford. It takes in the data that we get from the Spitzer Space Telescope that I just showed you, and it creates a forward model using the known parameters about the atmosphere of Uranus. Then it iterates over the forward model to get as close to the data as possible in something called a retrieval. And we do that by giving it priors, and because we don't want it to be too unrealistic. And those priors that we've decided to use are from the previous investigation by Orton et al. In 2014, but we are allowing them to vary because we're modeling the whole range of the Spitzer spectra for the first time. So these are the results that we're getting from our retrievals. We've done the low resolution and the high resolution retrieval. The low resolution is the red line, and we're getting a good fit across the spectrum for the low resolution. But we have some inconsistencies in the high resolution, and that could be for several reasons. It could be that the resolution of the data is actually variable with wavelength at these high resolutions, and we only have one resolution in the retrieval. It could be that we don't have the methane band to constrain things. And it could also be that during the reduction process, we've scaled and pivoted the individual orders to the low resolution because we trust that data a little bit more. So we decided to use the low resolution results in this investigation mostly. So the low resolution retrieval results here as the red lines, we've also managed to, we've allowed the acetylene and the ethane to vary. And as well as fitting the spectra, we've also managed to fit these gas temperature profiles pretty realistically. There is some deviation from the prior, but this all occurs at around the same stratospheric altitudes that I've highlighted in yellow here. And that could indicate that there is some degeneracy happening between the temperature and the gas abundances, but they're incredibly difficult to break. But because we have these realistic results that we think are reliable, that we can use them to investigate this longitudinal variability. So we've retrieved each separate longitude, and we see the same degeneracy between temperature and gas abundance. So what we wanted to do was try and break the degeneracy a little by setting up 3 hypotheses. So our initial hypothesis was that the temperature and the gases are allowed to change together. That's hypothesis A. And hypothesis B is that temperature is the only thing changing. Hypothesis C is that gas abundance is the only thing changing. And the plots on the right-hand side show the difference between the data and the retrieved spectrum. So hypothesis B looks very similar and has similar chi-squared, so our fits are similar as hypothesis A, whereas hypothesis C has higher chi-squareds over 1, so it's struggling to fit a little bit in the most extreme dim region of L3, and it drifts away from our allowed errors slightly. So what this is telling us is that it's more likely that it's a temperature change only rather than a gas abundance change only, and the temperature change only can fit just as well as when we allow gases to change as well. So we wanted to find out whether this temperature change only is caused by realistic temperature changes. So the left-hand plot shows the retrieval results for the temperature differences needed to cause the variation. And we see a small and realistic, around 3 Kelvin temperature change in the stratosphere, which is good and yet realistic. And on the right, we've also done a high resolution forward model using the low resolution results as priors, just to double check that this is working like we thought it would. And we have an agreement with that temperature change. So the modeled variation shown in red match the data variation shown in the blue and the green. So the temperature change only looks to be very possible. So we've also done some preliminary testing on the Neptune data. That's the next investigation that's going to happen, but preliminary results show that there is a less than 2% variation across the same species that we've tested for Uranus. And before we mentioned that Neptune is highly variable, it's dynamic, it's the opposite of it's the opposite of what we found. We found that there is very little variability in the Neptune stratosphere. So it might be the fact that it's too dynamic. So if we look at the left images in the near infrared, there's no one feature that stands out. Both hemispheres are going to look very similar. So this is part of a future investigation. So what about images of Uranus? If we've got these images of Neptune, maybe we can find out what's happening at Uranus as well using the same methods. Luckily, we managed to acquire some Keck 2 NERC2 images in the near infrared 4 days before the Spitzer data. So this is basically exactly what Uranus looked like during these 2007 Spitzer observations. And we have these two bands, the H band and the K prime band, and they sense around the tropopause or down to around 1 bar. And we see atmospheric features in both bands. So we have these features that have some kind of vertical structure, at least down at the tropopause. And another interesting thing is that we have 2 hemispheres in this data, one centered at around 80 degrees longitude and one centered at around 230 degrees, so the left and the right images. And the left one seems to be more active. It has these vertical cloud structures. And then on the right, we have sort of a dormant, less active hemisphere. And this meteorological activity in the left plot centers at around the coolest stratospheric emission. So it's consistent with this idea of large scale uplift. Another thing that we think may be happening, if it's not that, it could be some kind of stratospheric wave or something else in the stratosphere. These images from Mike Roman's work using 2009 VLT data show an apparent stratospheric spatial variation at around 13 microns in the acetylene band. And so what we see here is that we're seeing spatial variability in multiple bands of multiple instruments and multiple epochs. And speaking of epochs, is this always happening at Uranus? We also looked at the 2004 and the 2005 data that I mentioned before, and unfortunately the 2004 data is not usable for the variation analysis because there's too much noise, but the 2005 data shows a variation that is similar, although slightly weaker. It's around the 5 to 7% level, and but most of the variation is in stratospheric species, and then there's little variation in that tropospheric species. But it is consistent after that one full planetary rotation again. So something is happening. So this could be something that happens at Uranus all the time. The only way, though, to truly answer what's happening at Uranus, we won't be able to figure that out with the Spitzer data. We need spatial, what's it called? Spatial, oh, I've lost my train of thought, never mind. The only way to truly answer it is with the James Webb Space Telescope anyway. So it's still scheduled for launch on October 31st, 2021. And our team at Leicester has guaranteed time to observe both ice giants at multiple longitudes. And that's within the first 12 months of operation. So, and that's going to be using MIRI, which is the mid-infrared instrument. And that's an instrument developed in the UK as well, which is really exciting. So the James Webb Space Telescope, how is it going to help? So we'll be able to have spatial and spectral resolution at mid-infrared of both ice giants. And these field of views in the left plot make it look like the James Webb was literally built for the exact purpose of observing the ice giants in the mid-infrared. Maybe that's true. So for each image, we using the integrated field unit, or the IFU, of the MIRI medium resolution spectrometer, every pixel has an associated spectrum, and they're called spaxels. And we've already started the modeling process for a future paper that looks at what we might be able to see with Uranus. And here's an image of the pixel scale that we think we will have. So each one of these pixels will have an associated spectrum. So yeah, we'll generate spatially resolved global spectroscopic maps for the first time of the ice giants, which is really, really exciting. We'll be able to answer some of these questions. Another thing to be excited about for the future is missions to the ice giants. It's currently in the study phase, but there have been a lot of proposals and meetings and discussion, and it's definitely going to happen in the future, hopefully sooner rather than later. So 150 scientists from across the world met at the Royal Society in January just of this year for the Ice Giants 2020 meeting. So you can actually follow the progress of the Ice Giant exploration on Twitter at Icy Giants. You can also follow it on my Twitter. That's in the top right at Naomi Rowe-Gurney. And I'll leave you with the summary, and I look forward to any questions. Thank you.